Hey everybody, Mr. Withers here. Another week of geometry and another week of our favorite unit, circles. We have just 1 week left, 2 quick sections on circles. And then next week we're going to move on to probability and possibly a little bit on transformations. And then we're pretty much done. Just a couple days left that following week. And I'll keep you posted on kind of what that's going to look like as we get closer. So this week, circles, we've got kind of 2 little sections left. There's no retake this week. What I'm going to be posting instead is kind of I'm calling it a would-be test. This is what we would have taken if we were in school over trigonometry and circles. It is not graded. The answer key is posted. It's just kind of a chance for you to see kind of how you did understanding that. The first page of that, I will warn you, is tricky. Consider that more of kind of like an extension. Those were things that we would have gone over had we been together in person, but we did not go over in the online learning. Pages 2 and 3, you definitely should be able to do based on what we did in our videos and in our practice work together. So without further ado, let's jump in today with our circles lesson. 2 sections. I'm going to cut it in half for you and give you a good stopping point. So if you want to watch this in pieces, that's totally fine. This first section is called the power of a point. Not a PowerPoint like a presentation, but the power of a point. And specifically talking about a point that happens when we're talking about circles. So the first one that I want to look at is point P. So notice this is not the center. This is the center of the circle would be O. This is point P. And this falls on a line that intersects our circle. Now, here's kind of a theorem or a neat piece about circles that we need to understand, and that is the product of PA times PB is what we call the power of a point. So if I had point P and I knew my distances to A and to B, if I multiply those two values, I would find the power of point P. And power is shown in mathematics by, sometimes it doesn't even have these little tails on it. It's just kind of a square or 2 lines with a line over the top. Make sure that we differentiate between that and pi. This is not pi. It stands for product or power of point P. Okay, so that's a pretty simple one. Just multiply your 2 values. You've got that. All right. But we're going to move forward with a little bit more detail as far as dealing with points and how lines intersect today. So, power of a point rule. If we have a point P that is on line segment AB, or a chord, right? We've talked about chords before. And that point is also on another chord. In this situation, we're going to call it CD. Then multiplying the 2 pieces of both chords, they would be equal to each other. All right, and this makes sense if we think about that power of a point rule, right? PA times PB would be the power of point P, and PC times PD would also be the power of point B, and it would only make sense that those powers are equal if they're both intersecting that same point. So if we have 2 lines in a circle that intersect each other, you can multiply the value of each side, and they will be equal to each other. Okay, so this is rule number 1. This is the first thing that we really want to make sure that we understand today. And there'll be 3 segments in this first section. This is the first. Okay, so realizing that if we multiply, and I'll do a little color coding here for you. If we multiply PA times PB, that is going to equal PC times PD. All right, so we should be able to use that in example problems, and I'll show you one here in just a little bit. All right, rule number 2. This is, and yes, sorry, I forgot that I put that there. Yes, this always works. Always works. All right, rule number 2. We call this the secant segment theorem. In this situation, we have 2 secant lines. So they're not They're not chords where they're just self-contained within the circle. They're secants, so they're going through the circle, but they exist kind of on their own, right? They keep going. In this situation, notice that our intersection point happens outside of the circle. And so our equality looks a little bit different. Okay, in this situation, PA, right, the value of the entire segment, sorry, this should happen on the line, times PB, which is just the piece from our point to the edge of our circle. So we're not multiplying the two smaller pieces, we're multiplying the entire piece times the distance outside the circle that it falls. Okay, and this is going to be equal to, in our other segment, PC times, let me pick a different color here, PD. Okay, so hopefully you can see that. Essentially, we just want to multiply the whole piece, so how far from the point to the opposite end of the circle, times the distance from the point to the edge of the circle, the nearest edge, and those will be equal to each other. Okay, so this is our secant segment theorem. All right, so very similar that those products are going to be equal, but this applies when that point falls outside of the circle. All right, that is rule number 2. Rule number 3. Rule number 3 doesn't really, yes, this always works. Rule number 3 doesn't have a fancy name. We just call it in our book, Theorem 10.17. You could find various different names for it. You won't really need to know the name. You just need to know how it works. In this situation, we have a secant line and we have a tangent line. So if I were to name this, I'd call it something like the secant tangent theorem, something like that. Okay, so we have a secant line and we have a tangent line. And this rule tells us that if I take the value of that tangent line squared, so PD, it's going to equal PB times PA. So we kind of have half of that piece from our previous equation, right, where we said, all right, the distance just to the edge times the distance from the point to the other edge. Okay, but instead of finding, in this situation, the distance to each intersection point, because this is a tangent line, we only have one intersection point. So we could think of this like PD times PD, right? It's the distance to one intersection, like PB, and the distance to the other intersection, like PA. But in this situation, they're the same intersection point because it only intersects the circle once. So if you have a situation like this, we can just take PD squared, and it's going to equal the value of P to point B and P to point A multiplied. So let's do a couple examples. Yes, this always works. So example 1. This goes back to that first one. We just have two chords. They intersect at the same point, P, which falls inside our circle. Here's our given information. Okay, our given information, PC is 6. So we know that this segment has a value of 6. PB equals 5. So we know that PB is 5. PD is 15. Now, obviously not drawn to scale, right? I understand those look similar, and there's no way PD is 3 times that distance, but we're just using kind of random values here to practice. So we know from our theorem that, rule number 1, 6 times 15 should equal PA times 5, right? So we have our two segments on each side of the point. They should be equal to each other. If we multiply those together, 6 times 15, we divide by 5, we should find that PA is equal to 18. Okay, so this is just simple algebra once we get it set up. As long as we know our theorems and know our rules, there's nothing too tricky about it. Let's move on to another one. Example 2. So similar situation. This one goes through the center. Not a big deal, right? We talked about this theorem previously, where if we have a line that goes through the center, it's going to bisect that other chord. Okay. So in this situation, we see that PC is 20 and PD is 5. Now we're given in this situation, yes, this is a bisector. So I'm going to call these each X. So we know that by the power of our point, PC is 20 times PD, which is 5. And that's going to be equal to AP times PB. But we know they're both X, so we could think of it like X times X or X squared. So 100 equals X squared. A little simple math can tell us that those two segments should be 10. So this is 10 and this is 10. All right, that's enough practice with rule number 1. Let's check out rule number 2. So this one tells me, remember, we need to take the distance to my first intersection point times the distance to my second intersection point, and that should be equal in both situations. So here's my given information on this one. We are given that DC equals 12. We're given that PB equals 4. And we're given that PD equals 3.5. These are a little bit closer to scale. All right, so in this scenario, we know the entire length of PC, PD. Remember, we want to find that distance to the first point, so that's 3.5, times the entire distance. So this time I'm going to have to add 12 plus 3.5. I'm going to multiply times 15.5. That should be equal to, let's call this X, the short piece, 4, right, this one, times the entire piece, which is X plus 4. All right, so hopefully that makes sense, our setup, right? We just want to follow that formula. If I take 3.5 times 15.5, that gives me, let me change color here, that gives me 54.25. And if I take 4 times X plus 4, I end up with 4X plus 16. Simple math here, we're going to subtract 16 from both sides. I'll move over here. That leaves me 38.25 equal to 4x. When I divide by 4, it tells me x equals 9.56. All right, so, and it's technically 5625, which if you're going to get real technical, I believe is 9/16, if we want to go there, but doesn't matter. All right, so hopefully that makes some sense. Let's try another one. Example 4, here's that one secant, one tangent scenario. So we are given that PD is 10, and we're given that PB is 4. This time we're trying to find a smaller segment. All right, so let's see. PD is 10. PB is 4. Now, we're not trying to find the whole thing. We're just trying to find the one section. So let's see. We've got a formula that tells me PD squared should equal, I'll call this X, 4 times X plus 4. So I've got 100 equal to 4x plus 16. Again, subtract 16 from both sides. 4x equals 84. I'm going to divide by 4. And I find that x equals 21. So this segment here should equal 21. All right, so hopefully these seem simple enough. It's basically 3 rules, and we're just using simple algebra to apply them to different scenarios within our circles here. If you have questions on that, let me know. I would stop here and I would do some practice. So my suggested problems for you would be on page 754, 6 through 20 evens, and then do problem 21 as well. If you want to do more than this, you're welcome to. If you want to do less than this, you're welcome to. I've posted 754 on the website with the answer key as well. So this is a great point to kind of cut this in half. Stop the video here, do some practice, check your work, take a breather. Okay, if you want to come back later in the week to keep rolling, you'll just pick it up here at around the 16-minute mark. If you are feeling good and you want to keep going, then stay tuned. We're going to keep rolling here with our next section. And I will repost these practice problem numbers at the very end, along with the next section, so you can see them all together at the end of this as well. So don't feel like you need to pause and write it down if you're going to keep watching, but if you are going to stop, this would be a good stopping point. All right, those of you who are still with me, let's go ahead and move forward. This is section 10.8, and this is the kind of the finale of our circles unit. This is one of my favorite ones with circles because it's figuring out how do we actually graph a circle on graph paper. What does the equation look like? How do we build that? I just think it's really interesting. So we're going to start just kind of building from the ground up. When we first learned how to graph in pre-algebra, we started with t-charts. Okay, so we would find x values and we'd find y values and we'd plug things in. So one of the best ways that we learned how to graph was to find zeros. Okay, when we found zeros, we knew those were intersection points, right? Very basic. This is what you see here, an equation of a circle. Okay, it's a very basic circle, and we're going to take a look at it. It's a good one to start with. But what you'll notice is we have things being squared. And so anytime that we have something being squared, we know to get rid of it, we'll square root it, and that will give us two zeros because it could be a positive or negative. So when I find intersections on my x-axis, my y-axis, they're going to have two possible answers because of the positive and negative. So let's start with just finding some zeros. So if I plug in 0 for x, okay, 0 squared, obviously this is going to go away. I can just square root both sides, then I'll find that y could be positive 6 or negative 6. All right, now let's do the same thing, plugging in 0 for y. We know that's going to go away. You can see very quickly we're going to get the same thing. All right, so taking that knowledge now, let's throw it on a graph. Here we go. So if I take my first point, 0, 6, 1, 2, 3, 4, 5, 6, take my second point, 0, negative 6, 1, 2, 3, 4, 5, 6. Then I take my third point, 6, 0, 1, 2, 3, 4, 5, 6. And I take my fourth point, negative 6, 0, 1, 2, 3, 4, 5, 6. You can see this is the very beginning of, oh boy, this is kind of tough on an iPad. This is the beginning of what would look like a circle. All right, I have my perfect circle tool here, but it never quite falls where I want it to. So we'll just ignore that for now and go with my badly scribbled version. So in this situation, you can see my circle's center would fall right in the middle. Okay, and I have intersections on the x-axis and the y-axis in multiple places. Let's try one more in this way. The problem's going to look a little different here. So I've got 25 equals x minus 2 squared, x minus 2 squared plus y plus 1 squared. So again, we're going to make our t-chart. So I've got x, y, zeros. I'm going to find some zeros. We're going to kind of see where that lands us. So let's plug in 0 for x first. All right. So in this situation, I have 25 equal to negative 2 squared, which we know is 4, plus y plus 1 squared. So I have 4 I can take away from both sides, and I'm left with 21 equals y plus 1 squared. If I square root both sides, I'm going to get two answers. I'm going to get the positive square root of 21, and I'm going to get the negative square root of 21. On the other side, I'm just going to be left with a y plus 1. So in both of these, I'm going to have to subtract 1 to get that y alone. So I'm going to round here. The square root of 21 is around 4.6, I think. So positive 4.6 minus 1 equals 3.6. Negative 4.6 minus 1 equals negative 5.6. This is just approximate. Remember, we've talked in the past about how graphing isn't always our most accurate method because we can't get exact, but it's going to get us close. All right, now let's plug in 0 for y. Let me get rid of this. So here's my 0. Write out the rest of it. And we have a similar situation. So I've got 25 equals x minus 2 squared plus 1, right? 0 plus 1 squared. I'm going to take away 1 from both sides. So I have 24 equal to x minus 2 squared. If I square root both sides, I'm left with the positive square root of 24 and the negative square root of 24. Over here, I'm left with x minus 2. So I will have to add 2 to both of these to get the x alone. If I approximate this, the square root of 24 is around 4.9. So 4.9 plus 2 is positive 6.9, and negative 4.9 plus 2 is negative 2.9. So I've got 4 points now. I've got 4 zeros. Let's throw this puppy on a graph and see what happens. All right, so my first 0 is 0, 3.6. It's going to be around there. Okay, not perfect, but close. My second point is 0, negative 5.6. So somewhere around there. My third point is 6.9, comma, 0. So 1, 2, 3, 4, 5, 6. So really close to that 7. And my fourth point is negative 2.9, comma, 0. All right, so we can already see this is not centered perfectly on our graph. So this makes it really tough for us to draw an accurate circle because we don't know where our center is. We're just kind of guessing. Okay, and you can see that's close. It's not great. I would estimate my center to be somewhere around maybe there. I should have maybe come out a little more on this side. This is the tricky thing with circles and why I don't really like using graphing as my method for solving, because it's really hard to do by hand. Okay, but if we were to estimate this center, it would be, let's see, what is this? Negative 2, or sorry, positive 2, negative 1, somewhere around there. Okay, so you can see this is not exactly foolproof. There are lots of flaws in this system. So the good news is, just like when we first learned how to graph lines, when we learned how to graph parabolas, there is a system, there is an equation, and there is a simple way to do it. And that's where we're going to head now. So this is what we call standard form for the equation of a circle. In this equation, r is the radius of the circle. Okay, so the value that we see on one side of the equal sign is the radius squared. So if my radius is 5, what we're going to see on the one side of the equal sign is a 25. That's just the radius squared. X and y are just x and y. H and k are the ordered pair that represent the center. So in this standard form, H, K represent the center of our circle. We split those between the X and the Y. And R represents the radius. This would be a really, really good thing to have down in your notes somewhere. You will use this and you'll come back to it. Here's kind of the neat thing, just based on our last example problem. If you need to pause this to write it down, do that now because I'm going to go away from it. If we go back thinking about that, we said that our estimate for center here was 2, negative 1. X minus H, Y minus k. So our graph, our estimation, was really, really close to being accurate. In fact, we did estimate correctly, which is great. So r is radius, h comma k is center. Remember, these are minus signs, x minus h and y minus k, so just keep that in mind, that we're careful there. All right, so let's try an example. What is the equation of a circle with a radius of 10 and a center at 2 comma negative 5? Well, we remember our equation, radius squared equals x minus h squared plus y minus k squared. So I know my radius is 10, so 10 squared is 100. I have x minus my x value, which is 2, plus y minus my y value, so minus a negative, I'm going to turn that to a positive, 5 squared. And that's all the further we can go. This would be the equation of the circle. Now, you can see how this would make life a lot easier when we're graphing, because we would be able to just go in and say, okay, my center is at 2 comma negative 5. My radius is 10. So I'm going to start from that point. I'm going to count out 10 in each direction. Bam, got my circle. It's easy as that. Let's try another quick one. What's the equation of the circle with a center at 4, negative 5, and a radius of 3? So, there we go. So, radius squared equals x minus h squared plus y minus k squared. I know my radius is 3, so 3 squared is 9. I've got x minus my x value minus 4 squared plus y minus a negative, so plus 5 squared. And that is my equation. So when we are given the center and given the radius, this becomes very, very simple. Unfortunately, as you know, things don't always come out nice, neat, perfect, and simple. So we do want to make sure that we're prepared for some other possible situations. So let's take a look. What if we are given something like this, and they say graph the circle? Well, that doesn't look like standard form. I don't know what my center is. I don't know what my radius is. We've got some work to do. The good news is we are all very good at quadratics. And what I see here are some pieces of what could be quadratics. Okay, so if I think about that original formula, the radius squared equals x minus h squared plus y minus k squared. When I look at things like this, it reminds me of completing the square. Okay, maybe your brain already jumped to that, maybe it didn't, that's okay. But what we need to do to solve this is essentially just complete the square twice. So I'm going to kind of split this into two pieces. I'm first going to think about x squared plus 4x. If I were to complete that square, remember we take b divided by 2 and then square it. So I've got 2 squared, which is 4. So completing this square gives me x plus 2 squared. That looks like something that could be a part of a circle formula. However, I just added a random 4 to my equation. Technically, I did it right there. And I can't do that without also doing it to the other side. So I'm going to add 4 to the 11. On the other side, I have y squared minus 12y. If I were to complete the square here, I'd take 12 divided by 2, which is 6. I'd square it. So I'm going to add 36. Factoring this out, I have y plus, or sorry, minus, because that minus 12, y minus 6 squared. But again, I just added a random 36 onto the end of this equation, and I have to do that everywhere. So you can now see, hey, I've got a piece that kind of looks like that. I've got a piece that kind of looks like that. And because I've made some of these changes, I've got some extra numbers that also need to tack on to the other side of my equation. So when all this is said and done, if I take 36 plus 4 plus 11, I end up with 51. On the other side, I have x plus 2 squared plus y minus 6 squared. Holy cow, that is a circle formula. So all that we did was a little bit of rearranging, a little bit of completing the square, and it's really important to remember that these things get tacked on the other side as well, so that we're not just adding random pieces without doing it to everything. But everything we did here was completely legal. We just added it all to the same on both sides, and we're good to go. We just needed to somehow convert it to look more like the circles that, or the circle formulas, equations that we're used to working with. All right, let's do another example. All right, write the equation of the circle with the center at 1, 2, and goes through a point 0, 5. So let's think about the information we're given. I don't have a radius. I do have a center, x minus 1, y minus 2. So just based on the information that I have at my disposal here, I've got to figure out the radius. That's all that I'm missing. All right, and if we know the center and we know a point on our circle, the radius must be the distance between the center and that point, right? That would be true of any point in a circle. So, yep, you guessed it. We're going to need that old distance formula. I told you that it never goes away. I was not lying. So, not squared, subscript, x2 minus x1 squared plus y2 minus y1 squared. Let's plug those points in. So I've got 0 minus 1 squared plus 5 minus 2 squared. Negative 1 squared is 1. 3 squared is 9. So I have the square root of 10. So this is the distance from this point to this point, otherwise known as the radius of the circle. And fortunately, we're taking the radius squared. So if I square this, that square root goes away, and I'm left with a nice, neat 10, and my formula is done. So 10 equals x minus 1 squared plus y minus 2 squared. So you can see how much all of our old knowledge is coming back to haunt us here as we're dealing with circles. We've already had to complete the square. Now we've had to use distance formula. Take a look at this next example. We've got even another one coming back around. Let's think about this one. Write the equation of the circle with the endpoints of the diameter at 3, 2, and negative 1, 8. So in this situation, we're only given 2 points on the edge of the circle. We're told that they're a diameter. So we could take the distance between them, divide by 2, and that's going to give us the radius. But what that doesn't help us with is the center of the circle, right? Because we know we're going to need the radius. We're also going to need an x value and a y value for the center of our circle. So here's what I'm going to do first. I'm going to take these 2 points and I'm going to find their midpoint. That should give me the center of the circle, right? If I find the midpoint of a diameter, that should be the center. So I told you something else coming back we might have forgotten about, that midpoint formula. We take the average of our x values, x1 plus x2 divided by 2, and the average of our y values. That's going to give us our midpoint. So 3 plus 2 over 2, and, oops, sorry, I don't know where that 2 came from. 3 plus negative 1 over 2, and 2 plus 8 over 2 gives us 1, 5. So this is our center, the midpoint between this point and this point on our diameter. So now we have our center. So the good news there is we are done with half of our equation. R squared equals x minus 1 plus y minus 5. All we need now is the radius. And if you think about what we just did on the problem before this, we can just take a point on the edge of the circle and the center of our circle and find that distance. From the center to the edge, it's going to give us the radius. So again, distance formula, I'm going to take x2 minus x1. So let's call this point 1 and this point 2. So we've got 3 minus 1 squared plus 2 minus 5 squared. So I've got 2 squared plus negative 3 squared. Square root of 4 plus 9 equals the square root of 13. That is my radius. Good news again, we are squaring it. So that square root sign is going to go away. And I end up with a radius of 13. And next thing you know, we have a completed circle formula. 13 equals x minus 1 squared plus y minus 5 squared. So just in circle formulas alone, we have worked with quadratics, we've worked with the distance formula, we've worked with the midpoint formula. So you can see the further we go in math, the more these things start to tie together and we start to have to think back to things we've used before. All right, so my suggested practice for you on this section would be 760. I would do 1 through 9 and 13 through 21. Just go ahead and do the odds. This is from that other section from 10.7, I believe it was. So if you didn't pause the video, you've now got both sections listed here. This will be more about circle equations and formulas, and this will be more about those secants, tangents, and chords using the power of our point theorems. So this would be my suggested practice this week. Answer keys will also be posted so you can see those. Again, the test that will be posted on the website is not graded. The answer key will be posted with it. It's just a chance to see how you're doing on trigonometry, how you're doing on circles. If you run into trouble this week, please do reach out. I'm more than happy to help you. If you are someone who missed a retake, you can go back by clicking the button that says View Previous Weeks. Everything is still out there. It's still available. You can backtrack, you can review, you can do old assignments, you can do old retakes. It's all still out there, including the videos as well. So everything is at your disposal, including me via email. More than happy to help you with anything you need. All right, everybody, stay safe, stay healthy. Let me know if you have questions, and be well. We'll talk to you next week.